Okay, 7a, the solar system. First thing you need to know is that obviously the first model of the solar system that at the end of the day we accepted and people thought was true was from a person called Ptolemy, which is the geocentric model. Okay? The geocentric model specifically named because it has the Earth at the center. And in this model you have, if you look at a diagram of the model, you have all the planets up to Saturn. So in the same order, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, orbiting the Earth, including the Moon as well. The Moon is orbiting the Earth in this model. Something very strange and very different is that each of the planets, and the Sun of course is orbiting the Earth in the geocentric model, so the Sun is also going around the Earth. Each of the planets, except for the Sun, in their orbit around the Earth, is following an individual orbit as well. So they're orbiting around the Earth in the orbits that we still accept today for the heliocentric model, but as well as that, they're also orbiting in small circles as they're moving around. These small circles are called epicycles. You don't need to know that name for the GCSE, but it's obviously useful to be able to refer to. Otherwise, you just say, as the planets in the geocentric model from Ptolemy, the planets are orbiting in small circular orbits in their larger orbit around the Earth. Now, the reason that this geocentric model was proposed, accepted, and at that time made sense, it wasn't an unreasonable claim that things were orbiting the Earth, is because, and still to this day, if you do just look outside, and the only things you have to make up a theory for a solar system is your observation when you walk outside. You don't have telescopes, you can't, at the time you couldn't send spacecraft into space. You go outside every day, you see the sun rise in the east, you see it travel across the sky, and you see it set in the west. Every single day it rises above the horizon, it moves across the sky in front of you, and it sets. Same as the moon. The moon will rise, the moon will set. So from our perspective, as far as we're concerned, we're not moving, everything else is moving because we can see it moving. So why wouldn't you put yourself at the center of the solar system? So the geocentric model, the explanation for why would that model have been proposed, why was it widely accepted, is because they saw objects in the sky, not just the sun and the moon, but planets as well. They saw the planets moving across the sky. So this is why the geocentric model was proposed. Every single day you saw objects moving across the sky. You don't see yourself moving. Now, Copernicus was one of a few people who were the first people to say, this is not the correct model. They contradicted the geocentric model. They had to come up with evidence to support that. You couldn't just make a claim. This was so widely accepted that the church had accepted it, and anybody who had said, I disagree with the geocentric model, was either put in prison. For example, Galileo was put in prison for disagreeing with it. People were hanged, burned. It wasn't just something you could suggest. You had to prove it. Okay? This is the model, the diagram that we have of Copernicus, heliocentric, meaning the sun is at the center of our solar system, something that we know is correct today, we accept that still today. And he also had the same planets as the geocentric model, Mercury, Venus, Earth, Mars, Jupiter, Saturn, orbiting around the sun. Notice in both, that both solar systems only go as far as Saturn. The reason being, at this time, nobody had a telescope. You couldn't take observations of space with a telescope, only the naked eye, and the planets that you can only see with the naked eye go as far as Saturn. So Uranus, Neptune, Pluto at the time, they'd not been discovered at that point because they had no telescopes to see them. So both models agree, also on the order, except for the fact that the sun is in the solar system for the geocentric, they still agreed on Mercury, Venus, Earth, Mars in that order up to Saturn. Okay, so there are a few things that they do agree with. Obviously, the biggest contrast is that the sun is at the center of this one, the Earth is at the center of this one. There are no epicycles in the heliocentric model. Okay, Copernicus did not say that the planets, as they orbit around the sun, are also following small orbits of their own as they're moving around. And the moon was still orbiting the Earth in Copernicus' model as well. One of the most common questions you may have is literally just to compare and contrast those two models. Evidence to support this geocentric model at the time. What was it that Copernicus had seen to make him think that the sun was at the center of the solar system? One of the most famous observations that were made and is still made today was the retrograde motion of Mars, which is when Mars, you'll see it here, for example, in the sky tonight, you'll follow it over a few days, and then what will happen is it will seem to move backwards on itself, and then move forwards again. So the planet moves across the sky in this direction, moves back, and then moves forwards again. Okay, so at the time they're thinking, oh, hang on a minute, maybe it literally is what Mars is doing. It's moving around its orbit around us, and it's changing its direction, and then it's coming back again. But the explanation proposed by Copernicus was, well, if we're both moving and Mars is outside us, then we're eventually going to travel faster. We're going to undertake Mars. So if I'm coming in this way and Mars is out here on the outer ring, I'm going to look at Mars that way and see it in the sky over there. As I come over and I overtake it on the inside, I'm now looking at Mars, which has moved but not quite as far. I'm looking at it that way. Now if you're in the sky, you're going to see it there in front of you, you're going to overtake it, now you're going to see it there a day later, and then you're going to come back round, you're going to see it there again. It has not gone across, back and forwards, we just moved as well. So there's your explanation, or one of the explanations for that. Then came Galileo. The telescope was invented, or the device was invented. Galileo decided, I'll use that to see distant objects in space, make some observations. So he was one of the first people to make those observations with a telescope. One of the easiest ways to disprove the geocentric model, if the geocentric model says everything orbits the Earth, all you need to do is say, I can show you that something doesn't. For example, if every single thing in the solar system is orbiting the Earth, and you find one thing that specifically shows this is not orbiting the Earth, then you have disproved, or at least you've refuted the fact that not everything does. Galileo observed Jupiter over quite some time and noticed that it had small objects, natural satellites like the Moon, and those satellites were passing Jupiter at regular intervals, more than just one, and he concluded that there are moons that orbit Jupiter just like our moon orbits us. If you can say that there are moons orbiting Jupiter, then you can say that not everything orbits the Earth. Okay? So you can dispute the geocentric model by saying, I'm proving to you that not everything orbits the Earth. Alright, so there was one. Another thing that Galileo observed and monitored was the phases of Venus, just like the phases of the Moon. So Venus has phases based on the position between Venus, Earth and the Sun, which also helped support the fact that maybe we're all moving around the Sun. Alright? That's what he did. Current model of the solar system then. Everybody should know this at this point. You have the Sun, and then the planets closest to the Sun moving out. Mercury, Venus, Earth, Mars, Jupiter. Between Mars and Jupiter, you've got the asteroid belt, all orbiting around the Sun. Within the asteroid belt, not necessarily needed for the GCSE, but worth knowing, is a dwarf planet in there called Ceres. Then you have Jupiter, the biggest planet in the solar system, to Saturn, one of the most famous for its rings, but not the only one with rings. You've got Jupiter has rings, Uranus has rings, and Neptune even has rings. They all do, but they're the most prominent, so you can see those the most. Uranus, Neptune, and then of course Pluto, which was the 9th planet, which was then declassified to become a dwarf planet, as a result of the fact that just like Ceres, the reason Ceres is a dwarf planet, not because it's not big enough. Ceres is big enough that it is a spherical object. If you look at it in a photograph, quite easily it could be a planet. Pluto, we've got photographs now because we sent the New Horizons probe and it flew past, is a perfectly spherical object. Quite easily could be a planet. Okay? It's not because of its size, but as you can see with Ceres, there are other things orbiting with it. There's nothing in the orbit of Earth. We're big enough that we've cleared everything out of our orbit, we've taken it on ourselves, it's become part of our planet. Ceres is not big enough to have cleared its orbit, it's still orbiting with other things, so now it's a dwarf, it can't be a planet. Same for Pluto, we discovered later on that actually it hasn't cleared its orbit, there are still things orbiting around with it, so it was declassified. And then comets as well. Comets are one of the only things, as you can see, they're quite concentric. Both of the solar system models are concentric, and still to today we say that most of the planets will orbit around in very close to circles, some elliptical orbits, but around that same position. Comets are one of a few things that don't follow that trend. So for example here, if I wanted to draw the orbit of a comet, it could come in like this and go way out here. Okay? So this could be the comet at its farthest from the sun, comes in, slingshots around the sun closest, which is when we see it in the sky looking something like that, and then it flies off again, but it will go out really far out into our solar system at completely different directions. Okay? So we say that comets have highly elliptical orbits. Alright? Most planetary orbits are almost circular, but they're not. Even Earth looks like it's very close to a perfect circle, but still, they're all elliptical or oval shaped. Okay? But comets have the highest elliptical orbits of anything in our solar system. Thinking about how we make observations today, compared to the way that Galileo was making his observations, he had to look through the telescope and draw what he saw. Before that, they didn't have a telescope, they literally had to draw what they see and base their assumptions on that. Now we have telescopes, we can put them on the ground. However, you can only observe anything in the solar system if there is light leaving it and entering our eyes or our telescopes. The only light that's going to be able to enter our telescopes on the ground is that gets through the atmosphere. Any electromagnetic radiation that can pass through the atmosphere can be detected on the ground. Radio telescopes, for example, the image of the black hole that was released not long ago, using radio telescopes. Okay? So it wasn't even a photograph actually with optical light. They collected radio waves from the EM spectrum that arrived, and then they built a picture from that. Okay? Optical telescopes, because we know that visible light will pass through the atmosphere, hence the reason we see in the visible part of the spectrum. Infrared, most of it is absorbed high in the mountains. If you want to get a good image of an object in the infrared, you need to put your telescopes on the tops of mountains, for example, in Hawaii, Chile, places like that with large mountainous areas. They will put their telescopes on observatories high in there and observe the infrared. Anything that won't pass through, we can't see it on the ground. So if we want to look at objects that are only emitting X-ray, gamma or UV, a lot of UV can get through now, but not much. We need to make telescopes, send them into space, orbiting outside the atmosphere. We can make observations of anything emitting X-rays. Some of the biggest things that will emit X-rays in the universe are things like black holes. Alright, we know they emit radio waves, but they also do emit X-rays, things that we wouldn't be able to observe on Earth. So space telescopes are one of the best things that we have now to see even further into the universe. Not only that, we have computers, we can store data, we can transfer data, we can pass it on very quickly, and that's that. Alright?